Hello guys, Dimitri again, and today I'm going to talk about particle in the box. And the particle in the box is a quantum system that helps you learn more about wave functions and mostly about energy. It's the first actual quantum system you look at in quantum mechanics. So let me just starting off a reminder what the Hamiltonian is. Hamiltonian operator. So the Hamiltonian operator is basically double derivative, and double derivative is kinetic energy, and this is going to be the potential energy. So it's just h bar squared over 2m double derivative, which is just basically that whole thing circles just the momentum operator over 2m. And that will give you the kinetic energy plus the potential energy. So let's talk about postulate 5. So knowing this Hamiltonian operator will actually help you solve a time independent coordinate wave function. And this will just, I'll just say it again, solve the time independent Schrodinger's equation. And a Schrodinger's equation, I will show below, is just this. So by solving this here, we can get the wave function for any system. And this is only possible if we have the right boundary conditions. And with boundary conditions, we can solve for this wave function and find the wave function. So let me show you an example. Which is you're going to learn about is particle in a box. So imagine you have a particle, right? And it has infinite potential well. It's surrounded by infinite potential well. And this infinite potential well, and this is a one-dimensional, by the way. So it has a infinite potential well on the left and on the right. So it can't, if it tries to get out of here, it wouldn't be able to. It would just go straight, then bounce back. So it's only confined to that because of that infinite potential well. And inside the box, it has zero potential. So the particle has zero potential. So I'll show you here, and this is just the x coordinates here. It can go between 0 to L, which is the length of the box. And so the first, because the particle can't exit out of the box, its probability of being outside the box would be 0. So that means that the wave function when it's outside the box would be 0, because because 0 squared is just 0. And so it's 0 because of that infinite potential. And it's for outside the box on the left hand side. And for region 2, we don't know exactly what the wave function is. And we're going to solve the Schrodinger's equation. I'm going to show you next what the result is. And then it's just 0 to L, so it's just confined to that box. And right here, it has infinite potential. I'll just put v of x here. Sorry for sloppiness of the notes, but yeah, outside the box. So like on the right side, it has infinite potential, so we won't be able to get outside the box either. So it's just so the wave function is only inside that box. And I'll show you the result in a second. So from solving the time-independent Schrodinger's equation, you get this wave function here. Now the reason why you have this wave function is, I believe in your you're gonna go more in depth in your lecture if you haven't so already. It's because of that of sine. So when sine is at 0, when the wave function's at 0, it has to the box can't be at the barrier, like at on that edge of the box here. So it will be 0. And also because it has to be connected. The wave function here is 0, so it has to be connected at 0. So inside the box it must go towards 0 here. So at 0, sine of 0, it will equal 0. So that allows us to have that wave function be possible in that box. And so if it was at L, which I'll show this result here, that if it's at L, this will cross out and you would have n pi, which would equal 0. Now this n here tells you why it's 0. So it's going to be shown in your lecture, but I'll just remind you guys again that n is just integers, and it could be 1, 2, 3. So this particle can have an integer of can have an integer of 1, 2, or 3. So it depends on what quantum number you're looking at. And that's just what n is, the quantum number. I forgot to add that. So the particle could exist in different quantum numbers. So like, for one system, it can be n equals 1. For another, it could be n equals 2, and something like that. It can't be n equals 0, because if it's n equals 0, then that means the wave function would be 0. The wave function inside would be 0, and that can't be possible because the particles in the box. Not possible because particles in the box. All right. And so because n is integers, that's why up here that this will equal 0 at the edge of the box for any quantum number that's a whole number integer greater than 0. Okay, so let's move on to the next part. So if you were to apply the Hamiltonian operator on this, you would be able to get the energy of the system. Now, the Hamiltonian operator, you don't have to use you don't use the entire one, you just use the kinetic energy. Because think about it, the potential energy here is 0. It's already stated 0, so you don't include V of x here. So we're gonna just the Hamiltonian operator is only, just get a reminder, negative h prime, h bar over 2m with a second derivative. And I forgot to also mention that n is the normalization constant. So normalization constant is just normalize the wave function. I'll go more in depth later to see what that means. And you don't need to know the value of n to find the energy of this system. So h is going to be an eigenfunction of the wave function. So you only have this because the potential is 0. So you apply the operator onto the wave function, which would be y of 2, which would be inside the box, which would be h prime over y of n. And then you're going to find that, okay, let's just put h bar squared over 2m, double derivative, over n sine of n pi x over L. Alright, just go to my notes here. So I'm going to put everything here into a variable called w, and I'm just going to take the derivative of this. So it's just w of x. So now let's find the first derivative of this. And you're going to have only a single derivative left over, and you're going to have n cosine, because it's derivative, cosine of w x. And that's because and just a reminder, I simplified that variable if you guys get confused. Alright, and that's going to be a w on the outside. So that's what I extracted because w is on the inside. W, the derivative of wx is just w. And then we're going to take the derivative again, and you're going to get negative h bar squared over 2m. And you're going to also have a negative from the cosine, because the derivative of cosine is a negative sign. And you're going to have that, and then w squared, because you take another w out of there, and then you're going to have n sine of wx, which is the original function. And then from here, we would see that this is equal to, okay, just get this from my notes. So if we simplify everything and we square it, we would get that the energy that we can get is n squared pi squared h bar squared over 2ml squared. So to get the energy, we would need to know the quantum number, so the n for the system. We would also need to know the length of the box, and we need to know the mass. If we're to comparing two systems and they have the same length, the same mass of the particle and stuff like that, the only thing that determines the energy of the system would be n. So n determines the energy of the system. So that's why when we get the energy, we can just say the energy equation, E of n is equal to n squared pi h bar over 2 ml. So if this were to get excited, this would be able to reach the energy of, let's say, 1 to 2, so it could be 2 to 1, so everything will be the same, like length and mass. All right. Now next we're going to talk about is normalization. So normalization, so when you normalize a wave function, all you're trying to do is just make sure it statistically makes sense. So if I were to integrate over all space, I would have a wave function. If I were to integrate over all space for probability, then it'll equal 1, which makes total sense because it means 100% of probability of finding that particle. So let's just say, I'll just show an example here. So you have a wave function known as psi of x, and this is equal to n, and this is just an arbitrary function. And we want to normalize that, right? So we take the integral of this. So we know this is the normalization condition. And so to get this normalization condition, we just plug in, and then we get, so it's just a normal absolute value to get dx, and then we have n of x times n x. And so from there, okay, and then from there, we would see that this would simplify to the normalization constant is just a constant, so this is this and dx over, oh wait, and let's just say we know the value of this integral, and we call this the value of the integral I, and equals 1, so n squared times I equals 1, and then to find normalization constant, we just put I on either side. This will be 1 over I, and this is just n equals 1 over I. Alright, so if we were to try to find the value of this integral, we need to just find the value of the normalization constant. We have to find the value of the integral. So this integral here, we have to find the value of it, and then after plug it into this equation to find out the normalization constant, which will make the integration over, oh wait, I forgot to mention, you integral over all space equal to 1, which makes statistical sense, because if I were to go to this area, like all space, this is like, here's all space, I would go to this area, and this area, there's a 100% probability of finding that particle. Alright, so let's say we want to normalize the wave function for psi of n, which would be psi 2. So let's just say n squared. Now, all space, think about it, all space is within the box because the particle can't exist outside the box. So let's just consider all space being 0 to L, which would be inside the boundary condition for inside the box. And this is sine squared over n pi x over L equals 1. Now, how do we solve this integral? Well, we can use trig identities, and then sine squared of u shows that 1 minus cosine of 2u over 2. Knowing that, we can plug it into the equation, and for convenience, let's just make this equal to w for space, and let's just say n squared is 0, okay, 0 to L, sine, oh wait, not sine, but 1 minus cosine of 2u, no, 2w, so I just want to save it for space, and then this is over 2. I also want to mention too This is the result of squaring the wave function. I just want to, so if you guys don't get confused about that. So this is because of the squaring of wave function, because the sine of that, sine squared times, or sine times sine squared, n times n equals n squared. All right. So dx. Okay, then to solve this integral, this is equal to n squared, then parentheses. Okay, let's do 1/2 first. So this is, like, we can simplify to 1/2 actually, so it's much more easier. And this is x minus cos. Oh wait, integral that would be minus sine of 2w, and okay, yeah, sine of 2w, and this would be a boundary from 0 to L. So knowing that, I can plug in back the w. I'll just erase that and just plug it in back. Oh, and plug it back in. Just all right. Okay, that makes sense. All right. So let's say you're trying to solve this. So first off, we know that if we plug in, so the first is at L, so it'll be L minus sine, and this is just a result of plugging in L, so it'll be 2 times n pi x, and then this would be minus, because it's 0, plugging in 0 to x, you get 0, and then this is 0, sine of 0 is 0, so it's 0 minus 0, so it's just 0. And so all you have to worry about is here inside. So we know that n can only be integers, like 1, 2, 3. So that means this whole answer here will be an integer. So it'll be an integer times pi, which is always 0 for sine. So sine of any integer times pi is always 0. So that means that this is equal to n squared over 2. And then this is multiplied by an integer, so that's this whole thing is equal to 0. And that's times, oh, that's times L. And this is equal to 1. So we're gonna solve for 1. So we're gonna put L 2 over L on the other side. 2 over L. Take square root, and then we get radical 2 over L. All right, that's normalization constant. And when you plug it in to the equation, you get 2 over L times sine times n pi x over L. And yep, that should be a wave function that you're going to use. So you can use this for any, when you want to find a wave function for a specific n value, you just plug in like 2 or 1 or whatever, and then you get the wave function for that specific quantum number. All right, guys, that should be it. If you have any more questions, send an email or just shoot a comment. All right, guys, have a good one.